Hi everyone, this video is prepared to demonstrate our work, vCBIR, a verifiable search engine for content-based image retrieval. This work cooperates with Professor Xu and our PhD students. I will first introduce this engine and then show the demonstration scenarios. Okay, let's begin. With the increase of digital images, content-based image retrieval has been widely used in business. Image retrieval systems are huge and complex. Luckily, as the advance of data as a service, a small-sized company can build and maintain its image retrieval system on cloud platforms such as AWS. Here is a simple desk model. The image owner outsources its images to a service provider. When receiving a query image from a client, the service provider returns similar images to the client. Although this reduces the computation and communication burdens, the image owner loses control of the query processing. Therefore, result integrity is not guaranteed due to software or hardware malfunctions, or even hacker attacks. This security problem is quite pressing for some real business scenarios, such as product and medical image search. In our demonstration, we consider a malicious threat model. The service provider could return incorrect results, for example, faked or low-ranked images. The core techniques used in our demonstration are from our previous paper, Image Proof, enabling authentication for large-scale image retrieval, which has been published on ICDE 2019. Image Proof focuses on shift-based image retrieval, taking the advantage of the authenticated data structures. The service provider returns a verification object to prove that the results are not tampered with and include all correct images. Our engine provides two kinds of queries. The first is top K query. Given a query image, the service provider returns K most similar images. The second is the similarity query. Given a query image and a threshold, the service provider returns similar images whose similarity scores are larger than the threshold. Figure 1 shows the system architecture of vCBIR. The system consists of three parts: client, image owner, and service provider. Client has two modules: pre-processing module used to generate features, and the verification module used to verify the integrity of results. Image owner owns ADS module, which is to generate ADS. Service provider obtains authenticated query processing module, used to search similar images and generate VO. The main module is the ADS module, proposed in our previous paper. The ADS is built on shift-based image retrieval, which consists of two parts. Bag of visual words encoding uses randomized KT tree and inverted index search. The ADS consists of two components: Merkle randomized KT tree and Merkle inverted index with Cook filters. We have briefly introduced our vCBIR. Now we would like to show our engine under different scenarios. In the server side, for the first step, we can start our server with customized ADS settings on the top right panel. For example, we can set the number of feature clusters, 10,000. And we can also set the Merkle-Kitty trees for and the number of nodes. Then we press the Start button. We first show how to search similar images via vCBIR. In this scenario, we randomly select an image. This is the image of Eiffel Tower. There are two query models. We select top K query first. For example, we want the server to return top 10 similar images. We choose 0 for the scale and 1 sound features, which is then used to extract the features from the query images. Then press the Submit button. Observing the results, we can find that the resolution and the number of features extracted from the query image and the top 10 query results, which are ranked by the similarity scores. In each sub-image, we use a label to denote the correctness of query results. A tick denotes successful verification, and a fork denotes failed verification. In this normal case, we can find that all the query results are correct and complete. By clicking the View Proof button, we can see the details of view structure of query results. By expanding the signed root digest, there are 4 subtrees and 1 inverted index. Also, signed image digest proves the correctness of each query image. We can also search our query based on the similarity score. We set the threshold of a similarity score as 21%. We still choose the scale 0 and 1 sound features. And it actually returned 11 query results, whose similarity score are beyond 21%. By observing the view structure, we can find 11 verified signed image digests as the completeness and correctness proof. In the third case, we will show the effectiveness of number of features. Here we use the same image 10, scale we choose 0, and we alter the value of number of features to 2000. By adding the number of features, we can see that the query results are better than 1000 features due to the more precise feature extraction. We now show the influence of different scales. Here, we use the same image to search top 10 similar images and use 1000 features, but we alter the scale value to 1. The scale value 1 means to subsample the query image and get a smaller one. The higher the scale value is, the smaller the resolution of the query image is. This would reduce the image retrieval time. By reducing the resolution of query image, we can see that image retrieval processing is faster, and the result integrity is also guaranteed. Last, we show the attack scenario and how vCBIR protects the integrity of query results. First, we show the query results without attack. The images are correct and verified similar images. In the server side, we can also find the same information of query image and the results. We assume a malicious server provider wants to break the integrity of query results, such as replace or delete one images. In this attack scenario, the malicious service provider wants to, for example, replace the third image with another. We will show that our system will find this attack. We search the similar image again. We can find that the third similar image is associated with a fork icon, which means the query results is not guaranteed. From the proof, we can also see the verification of the third image failed. A malicious service provider may remove an image from the database without telling users. In this case, the client can also find this attack through VO. For example, the service provider removes the seventh similar image. We find that the last three images are marked with fork icons because their ranking is wrong. The VO also shows that the verification failed.